Hello, I'm Kazuhiko Minematsu from NEC Japan. The title of my talk is Parallel Verification of Serial MAC and EMOS. And this is a joint work with Akiko Inoue, Katsuya Moriwaki, Maki Shigeri, and Hiroya Tsukubo. To start with, let me show the CBC MAC, which is a classical message authentication code based on a block cipher. This picture shows CBC MAC, where E sub k here denotes the block cipher taking key k. It is probably secure for fixed message length and is efficient as it needs only one block cipher code to process one input message block. This property is also called rate 1. Although it is efficient in terms of the number of block cipher codes, it is totally serial, hence it has a poor performance for high-end systems having such as multi-core CPUs or SIMD instructions available. And this poor performance is because of the lack of parallelizability. So this gives rise to parallelizable modes. For example, PMAC for message authentication code and OCB for authenticated encryption modes. And this picture shows PMAC. As you can see, after throwing these L values here to the block cipher inputs, almost all block cipher codes can be done in parallel. However, parallel modes generally need more state memory than serial ones, and large memory is not desirable in the context of lightweight cryptography because implementation size is an important measure for lightweight cryptography, and in particular for hardware, state memory dominates the implementation size. That is, we face a dilemma. In fact, in the ongoing NIST lightweight cryptography, which is a competition for lightweight authenticated encryption, received lots of proposals that are inherently serial to save the size. So in this paper, we present a very simple solution to mitigate this gap, which we call pincer verification. It is a way to perform two-block parallel verification for serial MAC modes. It preserves the functionality of the original verification, so it can be used without losing security. We also extend it to A modes, and in this case, we may call our technique pincer decryption. We then provide some concrete applications of our technique and show implementation result. We take some NIST lightweight cryptography candidates and moreover two NIST standards, namely CMAC and CCM. For all cases, we almost double the performance. So I'll describe the pincer verification for CBC MAC because it is the simplest example of application. Okay. So given the tuple of M and T, the task is to verify if this equation holds. The pincer verification simply starts from the top of the tuple, namely M1, and the bottom, namely T. The forward computation path uses encryption routine, EK, while the backward path uses its inverse. Clearly, these two paths can be done in parallel and collide at some middle point. We just check if both paths yield the same value at the middle. this point. It is intuitive and trivial to see the functional equivalence to the regular verification. To be a bit more formal, the result of a pincer verification is identical to that of normal verification when the backward path is 1-to-1. That is, a permutation of T with a tweak consisting of the latter part of the message blocks here and the key K. Whenever this condition is satisfied, it holds a functional equivalence. The technique is applicable to the most of CBC MAC style modes as long as the tags is not truncated. We list such examples here. We also note that the technique cannot be applied to typical sponge-based MACs since they need tag truncation for security. So we also extend our technique to A schemes. For this purpose, we consider a general serial A structure. It is inspired by COFB mode. And this picture shows an encryption of general COFB. This low blocks here denotes a state update function that takes 2 input blocks and output 2 blocks. This chilled box is a tweakable block cipher that takes nonce and the block index and some domain separation bits as a tweak. Okay. And this picture shows its regular decryption. It uses an encryption function tilde-k, as in the case of the encryption, and a variant of row function called row f inverse here. Row f inverse decrypts the ciphertext block and updates the chaining value here. To apply pincer decryption, we need to define backward decryption shown here. It starts with tag T and uses the inverse of E sub tilde E sub K and a new variant of row function called row B inverse. The row B inverse decrypts the ciphertext block and inverts the chaining value. Note that this variant may not exist and it is needed, as it is not needed regular decryption. So we have an additional condition for row function. The pincer decryption computes the forward and backward computation passes in parallel and checks if both passes generate the same chaining value at some middle point. To see when pincer decryption works, we need to introduce an extension of tweakable block cipher called tweakable block cipher with auxiliary output. We do not need the security definition for it because we introduce here to just for functionality. The definition is here, and I'm not going into the detail, but this B value here denotes the auxiliary output, and the S denotes the message here. We need to, for the encryption function of the TBC-AO is denoted by hat-E here, and we need 2 variants of decryption routines, hat-EF inverse and hat-EB inverse. The former only inverts B, but the latter inverts both B and S. This definition is in fact a generalization of the tuple of row and row F inverse and row B inverse. Suppose our target AE can be described as a composition of two TBC-AOs F and G both taking variable input length message as and a chaining value. Then it allows pincer decryption as shown by this picture. So this part shows the regular decryption using the both the forward inverse functions and the pincer decryption. For pincer decryption, this G function uses the GB inverse to invert the state value from here. It preserves the correctness, and we call such an A a serial A. Next, we show 3 case studies for our technique. The first one is ROMRAS, which is a finalist of NIST lightweight cryptography competition. Its structure is similar to COFB, but it is TBC based. The underlying TBC is skinny. Its primary member, called ROMRAS N, and it can be described as a serial AE defined in the previous slide, so we can apply the pincer decryption. We implemented ROMRAS on ESP32 made by the Expressive Systems. It is a dual-core 32-bit microcontroller, and it's popular for Internet of Things applications for its built-in Wi-Fi and Bluetooth. Our implementation of pincer decryption follows the straightforward strategy, namely, we use one core for forward computation path and the other for the backward path. After some optimization for task switching between 2 cores, we obtained the performance figures shown in this table in cycles per byte. This shows that if message is long enough here, we can halve the decryption cycles. The second case study takes CMAC. It is a NIST standard MAC mode specified with AES. It is based on CBC MAC, but is different at the process of last block here. We implement CMAC on Intel CPUs having AES instructions called AES-NI. And for such CPUs, it is known that we can parallelize the block cipher calls by interleaving the AES instructions. So because this hides the latency of instructions, this technique is quite common. But of course, it is possible if the mode itself is parallelizable. Counter mode is a popular example where we can interleave AES encryption instructions or AES decryption instructions. In our case, we need to interleave one AES instruction and one decryption instruction. We tested, and in fact, it works. So we can reduce latency by using the pincer verification. Okay. This table shows the implementation result on an Intel Skylake processor. For both message of for the message of length 1 kilobyte, the number of cycles roughly halved by pincer verification. We stress that this is achieved on single core, and it is a speed record for CMAC verification on Intel for single core and a single message. The third case study takes CCM. It is one of 2 NIST standards for AE, and the other is GCM. CCM is a composition of counter mode and CBC MAC in a Mach-Zehn encryption composition style. It is quite widely deployed, such as Wi-Fi and the internet and IPsec and so on. It is generally slower than GCM, but it is simpler in the sense that it does not need a full field multiplier that is needed by GCM. Actually, CCM is not what we call serial AE, but we can still benefit from the pincer verification, pincer decryption technique. This picture shows the decryption of CCM. Using this, let me describe the known decryption strategies for CCM. The easiest one is for us to perform a counter-mode decryption in parallel here. Then perform CBC MAC regular verification in serial here. A more advanced strategy is interleaving one block CBC MAC verification and one block CTR decryption. So we perform one block here and one block here in parallel. So it was employed. This implementation strategy was employed by OpenSSL. Because this B sequence is roughly a concatenation of nonce and associated data and message. So such interleaving is possible. Our pincer decryption for CCM is to combine the interleaving and the pincer verification of CBC MAC. Depending on the available number of parallel units denoted by S here, we have two options. The first option is first interleaves counter-mode decryption and regular verification of CBC MAC. And when counter mode is done, it switch to the pincer verification of CBC MAC for the rest of input. So this option works when S is larger than 2. Yeah, this picture shows how it works, where green boxes are assumed to be computed first, and then we compute the red lines here in parallel until it reaches to the end of the counter mode decryption. After that, it performs the pincer verification indicated by blue lines, namely it starts with in the middle of this B sequence. The second option combines the pincer verification of counter mode and pincer verification of CBC MAC. Here, pincer decryption of counter mode means we decrypt the top and bottom ciphertext blocks. It is faster than option 1, but needs S larger than 4. And this picture illustrates how it works. After computing these green boxes, we can compute these 4 red lines in parallel. This table shows the required number of block cipher codes for each strategy. It shows that option 2 mostly halves the number of the block cipher codes from the plain interleaving strategy. We also implement the regular decryption and pincer decryption option 2. The environment is the same as the case of CMAC, and the CPU there allows S being 4 from the latency figure of AES instructions. The results shows that speed up of a factor around 2 in case of the 1 kilobyte message. As with the case of CMAC, this is a speed record for CCM decryption on Intel CPUs for single core and single message. To summarize, we show a very simple two-block parallel solution to verify or decrypt serial MAC and A modes. It is widely applicable to CBC MAC-like MACs and COFB-like A schemes. And as we have shown, it is also effective to other A schemes such as CCM. Our implementation result for CMAC and CCM on Intel CPU shows the speed record for single core. So to conclude, there are some future topics, such as implementing CMAC and CCM on ARMv8 64-bit processor where AES instructions are available. The other one is application to other generic composition like AE mode, such as SIV. Finally, it would be interesting to consider if we can combine bit slicing or fixed slicing technique with our technique. Typically, these techniques are used for parallelizing block cipher encryption or decryptions, but what we want is a way to parallelize encryption and decryption. It seems possible if the block cipher has a great similarity in encryption and decryption, say by using a FISO, and this might give us a way to boost the performance of non-AES-based MAC or A schemes on single-core CPU. Okay, this is the end of my talk. Thanks for listening.